Shall we start? Good morning, everybody. Some of you have experienced an experiment on Bernoulli's law this morning, entering this room. I don't know what made the air condition go haywire. So now I've blocked this door, which reduces the flow speed dramatically, as you see. All right. What's the point for today? As announced, I would like to summarize the lecture and answer your questions if you have any. So let me first go through the lecture. And I'm projecting the table of contents here of this book so that, if needed, we can refer back to the respective chapters in the book, but I think I pointed them out as we went along. So this lecture had 5 parts. Number 1, radiation processes. Number 2, hydrodynamics. Number 3, plasma physics. Number 4, magnetohydrodynamics. Number 5, stellar dynamics. Each of them had 3 parts. All right, so let me abbreviate them. Radiation processes. Hydrodynamics. Plasma physics. I'm not doing very well, but we get to it. Magnetohydrodynamics. Stellar dynamics. All right. Symmetry is badly broken. Let me go through the parts of 1 to 5 that I wanted to highlight particularly. Number 1, I wanted to speak about continuous spectra. And there, as I'm sure you remember, the 2 main foundations were Larmor's equation for the radiation of an accelerated charge and the Plancherel equation, right, that relates a spectrum, which is a Fourier transform, to the radiation power. So continuous spectra Compton scattering. And with this, I want to include Thomson scattering, and the Thomson cross-section, because it appears everywhere. And finally, line spectra. All right, and as we saw, going along this part number 1 of the lecture, with Thomson scattering, we did not take momentum transfer on the scattering charge into account. With Compton scattering, we did. We still considered Compton scattering in the classical limit, that is, in the limit of a classical electromagnetic field. If you have the need to also quantize the electromagnetic field, then you arrive at the Klein-Nishina cross-section. The question came up, why did we use the Thomson cross-section in order to quantify the total Compton cross-section? is answered when you go to Klein-Nishina scattering and you see that the Thomson cross-section applies also there. Okay, line spectra. Well, first of all, I wanted to connect the theory of line spectra to ordinary lectures in quantum mechanics and theoretical quantum mechanics. And then I wanted to highlight the processes that determine the width of spectral lines and the curve of growth that relates from there. I also wanted to introduce the notion of an oscillator strength, because that appears frequently in the literature. These were the main pieces of content for the for part number 1. Part number 2, hydrodynamics. First of all, I wanted to take care to trace back the origin of the hydrodynamical equations. And if you remember, they turn out to be conservation equations. They are conservation equations because even though we assume that there are scattering processes, in fact very many, that all of these scattering processes conserve certain quantities. And based on that, we could derive the hydrodynamical equations. And here I'm including now the hydrodynamical equations with and without viscosity. And as we saw, viscosity is a transport effect. So it's the transport caused by the transport of momentum over finite ranges. So it arises only when you relax the idea of ideal hydrodynamics, where the mean free path is assumed to be infinitely short. Okay, so the origin of the hydrodynamical equations, that was the first important part. Then what I wanted to highlight and to use frequently here is linearization and stability analysis. And this came over and over again, and we used this here in hydrodynamics to study sound waves, which we needed in order to understand shocks, and also the fundamental origin of sound speed. So linearization and stability analysis, this was an important part here. And finally, I wanted to discuss methods to arrive at hydrodynamical statements without solving the hydrodynamical equations. That was a big point, right? We used this in 2 circumstances. The first one is Bernoulli's equation, which we have experienced this morning. And we didn't need to solve the hydrodynamical equations there because the Bernoulli equation is the first integral of the Euler equation. Right? And so let me write down, what do I write down? Bernoulli. And of the many Bernoullis, I mean Bernoulli's equation as it appears in hydrodynamics here, but also the shock jump conditions, right? These are also statements about hydrodynamical flows which avoid solving the hydrodynamical equations, right? Because we, first of all, saw from the stability analysis that there must be shocks. The reason for shocks to occur was that the sound speed increases as the density increases, so that sound waves steepen. So in the hydrodynamical situation, you create discontinuities, and at these discontinuities, whatever they may look like, the conservation laws continue to hold. We had a problem on that for relativistic flows, and we treated them in the lecture for non-relativistic flows. So the shock jump conditions, from my perspective, fall under the same category here, hydrodynamic statements without solving the hydrodynamical equations. Symmetry is broken. Number 3. Plasma physics. The first and important thing we did was to look at scales. I'm going to make a comment on that afterwards. What scales did we have? We had a length scale, we had a time scale, we had a frequency scale, which of course is just the inverse of the time scale. And they turned out to be important all along. Right? We derived the Baye length. And I'm going to write down here now Yukawa shielding. That's not a very correct term, but you know what I mean, right? It's the shielding of the potential of an electrostatic charge such that its effective potential attains Yukawa shape. All right. Then we had Landau damping. And even though this was only a small part of the lecture, it's important for the whole concept because it shows the relation between an imaginary part of a response function and dissipation. And this is the first indication that a huge field of statistical physics, namely the field of fluctuation-dissipation relations. Right? And this was one way of attaching this whole field to this particular lecture. And if you want to know more about this, then there are thick books about that. Also, Landau damping appears again in stellar dynamics. As you saw, the response function there is exactly the same as in plasma physics. So dielectric response theory, this was the next important part. And since that was all based on Liouville's equation, as stellar dynamics is, right, it of course appears there in exactly the same manner. All right, number 4. Magnetohydrodynamics. We had the induction equation in 2 variants, right? We derived it first as everybody does it, and so that now we get away with a homogeneous equation, which can never explain the origin of magnetic fields. Right? Because if you start with 0, you stay with 0. And therefore, towards the end of that section, we saw how you can create magnetic fields if you mix at least two species of particles. Right? And then you can get an inhomogeneity in the induction equation and create magnetic fields. So that was that. And we had the back reaction on the plasma flow. 2 essential things, right? Magnetic fields don't want to be bent, and they don't want to be squeezed. And this gave rise to a whole bunch of interesting plasma reactions to magnetic fields, as we saw. Okay, that was that. Then we looked at wave propagation in magnetized media. And to make things simpler, we assumed that we have a cold plasma. In other words, a plasma in which the thermal motion of the electrons is slow compared to the motion in the magnetic field. We restricted ourselves to cold plasmas because otherwise it would be too complicated for a lecture. Right. And the main issue there was that even though the methods were essentially the same as those that we used in dielectric response theory, we acquired an additional complication by the magnetic field setting its own direction in the plasma. Yeah. Yeah, it's the book on plasma physics by Ishimaru, for example. There must also be books by Balescu about this. C or S? I can give you the book from my office if you need it. Huh? Okay. So, and finally, again, right, we made a stability analysis. In exactly the same manner as we made it in hydrodynamics. And we saw that now we have a much richer spectrum of different types of sound wave. We had, for example, and that's what we started with, the Alfvén waves, which are not driven by the thermodynamic pressure, by the magnetic pressure. And we saw that even thermally driven sound waves split up into two branches, right? The slow and the fast waves. And otherwise it would be too simple. Those modes can mix, of course. And then you have a lot of fun. All right. 5, stellar dynamics. Again, we looked at scales. Right? We wanted to see what is the main difficulty introduced in stellar dynamics is the infinite reach of the gravitational interaction. And therefore, we took some care to understand what the relaxation time for stellar dynamical systems is. Under the assumption that we can neglect collisions, right? In other words, under the assumption that the relaxation timescale is very long, we could derive Jean's equation. But this also shows that Jean's equation, as frequently as it's being used, has its severe limitations. Right? They are made for collision-less stellar dynamical systems. But whether or not a stellar dynamical system is collision-less depends on the specific conditions. Okay, then we had dynamical friction. And finally, and this was a bit outside the scope of the lecture, we talked about what you can do if you have to give up the assumption of a collisionless stellar dynamical system. Namely, we had a look at the Fokker-Planck approach. We saw that this is an approach that is based on diffusion in momentum space. And if you restrict yourself to first order diffusion only, then you get nothing. And so you have to go to second order, so you have two diffusion coefficients which are related to each other under equilibrium conditions. And this allows you to essentially write down diffusion equations with a single remaining tensorial diffusion coefficient that you can then progressively simplify. All right, you see, Ishimaru stands around here. Good. So that was the plan of the lecture, right? These 5 parts with 3 main pieces of content each. Now remember what all of this was based upon. 5 parts, right? Mechanics, electrodynamics, quantum mechanics, thermodynamics, and statistical physics. Maybe let's use another board for that. So now without names, right? You have the names above. We had electrodynamics, Maxwell's equations. We used them in several places. First of all, we used them to derive or to rederive Larmore's equations. I'm speaking of equations because we used them in 4 different ways, right? We either had the differential or the integrated Larmore equations, and we had them either non-relativistic or relativistic, so 4 of them. And this was a whole procedure, right, that started with the retarded Liénard-Wiechert potentials, but traced the whole thing back directly to Maxwell's equations. We used Maxwell's equations again, of course, for plasma physics, where we used them in media, and we used them again for magnetohydrodynamics, obviously, because we needed the Lorentz force. So they reappear everywhere here. We used classical mechanics, okay? Of course we use classical mechanics. What did we use it for? Of course for stellar dynamics, right? For studying the Hamiltonian dynamics underlying the dynamics of stellar systems. They also enter into hydrodynamics. I do not enter so much into 3 and 4. Yeah. We used quantum mechanics, of course, in order to understand line spectra. And what did we use there? Well, Fermi's golden rule. No more, no less. What is Fermi's golden rule based upon? It's an integral of Schrödinger's equation. Right, so, as I said, it's a little bit unfair to write Fermi there. First of all, because you write Fermi in very many places. But this doesn't matter. Okay, this is Fermi's golden rule. What enters everywhere here from classical mechanics is essentially the symplectic structure of the Hamiltonian equations. And very rarely did we need to know what the Hamiltonian function really looks like. But the symplectic character of the Hamiltonian equations we used frequently everywhere when Liouville's theorem was entering. All right, 1, 2, 3. Thermodynamics. What the hell did we need thermodynamics for? In the hydrodynamic section, right, we used it to study adiabatic expansion or compression. We used it to relate the adiabatic index to the microscopic structure of matter, because we count the degrees of freedom. But we also used it to distinguish between the adiabatic indices that you expect in relativistic and non-relativistic flows. And we saw, okay, the relation between, let's say, entropy and the number of degrees of freedom is just a factor of a half, right? And this is because the energy-momentum relation in non-relativistic physics is quadratic, and in ultra-relativistic physics is linear. And this gives rise to a whole different, to different behavior. For example, in hydrodynamical shocks. We also used Maxwell's relations, do you remember? Right? When we talked about the sound speed, we used Maxwell's relations. So that entered into hydrodynamics. And then statistical physics. Where the hell did this appear? Liouville's theorem, of course, right, for example. And Liouville's theorem entered here, and so on. And again, right, we also use statistical physics in order to count or to relate the number of degrees of freedom to, for example, gas dynamical properties. We also made frequent use of the equipartition theorem. Right? We wouldn't need to have done so. We could have directly integrated, for example, the Maxwellian velocity distribution and so on. But of course, the equipartition theorem makes this much easier. And of course, right, we often used thermal distributions, which directly come from statistical physics and thermodynamics here. All right, in that way, the diagram, of course, looks a bit awkward, but the way how you can relate astrophysical processes to the foundations that you know from the basic lectures in theoretical physics, this is the main idea of this lecture. Right? So in order to understand how do I relate electrodynamics to radiation processes, how do I relate classical mechanics to stellar dynamics and hydrodynamics, how do I relate quantum mechanics to line spectra, essentially, where do thermodynamical properties enter into hydrodynamical flows, for example, where do principles of statistical physics enter? All of that is the foundation here. Now, if you wonder what exactly did we need from fundamental theoretical physics for theoretical astrophysics, it's not too much. Right? It's Fermi's golden rule, it's Maxwell's equations, and Larmor's equation in particular. It's the Liouville equation, and there are some fundamental thermodynamical relations. Not much more than that. And out comes a very rich structure of foundations of theoretical astrophysics. All right, so this was the, so to speak, the construction principle and the idea behind this lecture and the main contents. Now let me say a few things about the purpose of the lecture. As you have noticed, this is not about astrophysical or astronomical objects. Okay, this was of course completely on purpose. Right? The idea is to enable you to study objects of your choice on your own, right? And to have a set of tools available whose origin you understand. That's the main point, right? To enable you to interpret astronomical phenomena on your own. And at the same time to know the limitations of the conventional assumptions. That was also a very important part of this lecture. As I said many times, and I'm going to say it again, there's nothing bad about assumptions. You can't avoid them. But for Christ's sake, make them open, right? Make them explicit rather than hiding them underneath some rug. So it's very important also to understand what are the limitations of all of these concepts and their applications everywhere in astrophysics, right? Where can I use the standard approach and where can I not, right? Where do I have to be careful? And we saw the limitations everywhere, right? For example, if you go back to hydrodynamics, you are assuming that there are microscopic conservation laws. Well, this may or may not be true, right? For example, if you have reactive flows, you might create particles through chemical reactions in a hydrodynamical flow. every combustion is an example for that, right? And so on and so forth, right? We spoke about the assumption of collisionless dynamics in stellar dynamical systems. We spoke about the fundamental scale hierarchy in hydrodynamics, and so on and so forth. Right? So this was also an important purpose of the lecture, for you to see where are the limiting assumptions, or what are the limiting assumptions, and where would you have to be careful if you want to apply these equations. Because if you apply these equations, you necessarily copy the assumptions that have been made in deriving these equations. This may or may not be appropriate. In many cases it is appropriate, but do it consciously, right? Apply these equations consciously. And put other results into doubt. This is also an important part of this lecture, right? If somebody presents you anything and says, here is the conclusion usually comes with a whole catalog of restrictions due to the assumptions that have been made. This is fine if you make them explicit. All right, good. Now, over the years, and increasingly over the last years, I hear comments like, why do we do all that? Because artificial intelligence knows how to do that. Okay, fine. Let me then first make a comment on the term artificial intelligence, because intelligence derives from the Latin word intellegere, which means to read in between, and what is meant is to read in between lines. Well, this is exactly what artificial intelligence does not do, right? Because it reads exactly along the lines. And therefore, all that artificial intelligence gives you is an interpolation of existing knowledge, or an interpolation between things that people have written because they thought this is existing knowledge. And artificial intelligence will increasingly copy itself, right? Because the productivity of artificial intelligence is of course very much higher than human productivity, and therefore very quickly now artificial intelligence is going to feed upon itself. You probably know the effect of the video camera watching its own output, right? It will be completely detached from reality. So, yeah, this lecture is meant to enable you to use your own intelligence and to go beyond what artificial intelligence finds by interpolating between productions of human intelligence, or increasingly of its own. Okay? So there is, of course, a purpose in knowing about these things, and not to ask artificial intelligence. Good. If you like, forget the past few sentences. Of course, they have nothing to do with this particular lecture. They have a lot to do with my understanding of what lectures are for, but okay, fine. Questions? Yes?
I actually have a question about hydrodynamics and just some terms that we used on the exercises and that were extremely mixed up in our tutorial. So maybe you could just sum up again what exactly is meant when a hydrodynamical system is stationary or static, because we use that in many different ways and I'm a bit confused.
Part of that confusion is intrinsic. This is the typical distinction between the two. What else did you say? Static, stationary, there was something else.
Well, I mean, a combination of those, but it's like when you say del, so partial derivative by t is 0, do you mean partial derivative of position, of velocity,
Yeah, I mean, hydrodynamics is a theory of three things, right? The density, velocity, and the pressure. And so what I mean is that these apply to any one of them, maybe exclusively, which would mean that you could have a flow that has a static density distribution, but a stationary velocity distribution. Right? This could be, for example, if you have a hydrodynamical system which has essentially, which is spherically symmetric and has radial flow, right? You can have a situation in which the density is completely static, but a lot of motion is going on underneath. So yes, what is meant by that needs to be specified, right? So do you mean this or that or that? Yeah. Exactly, yes. Yes. So you mean this equation, right? Yes. Watch out for the limitations. First of all, yes, this is a single scattering event. Second, it is valid in the rest frame of the electron. And that means the rest frame of the electron before the crash. Right? When we spoke about the Fokker-Planck approximation last week, we already went beyond that, right? Because there we were assuming that the electrons are also moving. Right? So this is a frequently used formula for the energy change of the photons in quantum scattering events, but under rather far-reaching assumptions.
My second question is, could you maybe explain why the Alpine mode or the modes mix? Because I did not see it in the equation.
Yeah, what I meant is that the fast and the slow modes mix. Ah, I see. All right. So if you look at, it's interesting, by the way, to go through one's own book after a while. Because then you look at these equations and think, this can be derived so much more easily. Anyway, here you see, indeed, in this particular frame of reference, the Alfvén modes single out completely. But the fast and the slow modes mix. And that's what I meant, right? You have here this 2x2 matrix that whose subdeterminant gives you the dispersion relation for the fast and slow modes. That contains off-diagonal elements. Right? So they mix. But of course, you can introduce a different reference frame in which you could also separate different, you could separate the fast and slow modes into different branches. Right? Or you could introduce a different reference frame in which the Alfvén modes are being mixed into the other ones. Right? So the fact that here the Alfvén modes are so cleanly separated is a consequence of our choice of reference frame. If you diagonalize the whole thing, you get two different branches. And this is something we did below, right? When we found these two types of dispersion relation that separate here. They don't need to, depending on the reference frame. Was there a third one? Go ahead. Go ahead.
Could you maybe explain what the lines are in the website X-ray?
All right. Yeah, important. Okay, where are we? So you refer to this picture, right? They are excitation lines of deeply lying atomic shells. Right? The different types of metal species, metal in the astronomical sense, right? Everything heavier than helium is a metal. Unbelievable. Okay. Most of these atoms are heavily ionized. So, for example, I think there is an iron 13 line or something like this. And so the remaining electrons in these highly charged ions are very tightly bound. And so their spectral lines, if you manage to excite them, fall into the X-ray regime. And so you have X-ray emission lines from the tightly bound electronic bodies, so to speak, of highly charged ions. And they are extremely important for X-ray astronomy. And for example, this one is an iron line. It's a very famous iron line. I think that's from iron 13 or something like this. And it's around 7 kV, I think 7.4 kV. And of course, people have nothing better to do than search for that, because the excitation state of that particular line, without any other lines nearby, right? So without interference from them, tells you important things about the plasma. And then you have additional lines. So I made this plot here with the XPEC package as written underneath, with a Raymond-Smith plasma model with a certain mixture of species. And then you have a whole bunch of X-ray lines from silicon, sulfur, oxygen, all kinds of things. So there is one left.
Yes, and it's more out of personal interest, but you mentioned that rarely tailor its ability to do something with supernovas of white stars.
White dwarfs, yes.
Could you explain a bit more what happens?
Yes. I think there's a nice picture, isn't there? Okay. What happens is the following thing. You have a white dwarf. And a white dwarf is something very strange. I mean, it's being stabilized by the degenerate pressure of the electrons in the core of the white dwarf. So it's very important that the whole stability of the white dwarf against gravitational contraction is being provided by something non-thermal. All right, now, white dwarfs are really sensitive subjects. And in particular, they don't want to be overfed. And if you overfeed them, the whole material in the core is being further compressed. And then you can reach conditions in which, due to local density fluctuations, suddenly the remaining material, it's a mixture of carbon, nitrogen, and oxygen, goes above the thermal fusion limit. And then in various random spots in the interior of the white dwarf, suddenly the whole material starts burning. But it can't expand, right? Because the whole pressure is provided by the electrons. And so you create suddenly very hot material which forms bubbles that are very hot, underdense because of because they are expanding in a very dense environment. And suddenly you have created a situation in which lighter material, specifically lighter material, finds itself underneath specifically more heavy material. And this will start overturning this. And this gives rise to an extremely violent reaction, right? Because as you saw, as you see here in this picture, the Rayleigh-Taylor instability just makes the material burp, right? And then once the lighter material is rising up, you get this Kelvin-Helmholtz instability at the boundaries. And that mixes unprocessed material into the burning substance, and thereby increases the surface of the burning front dramatically. And then, as Loriot would put it, es macht Puff. Ne? Und all die weißen Zwerge gehen kaputt. All right? It's a pity we can't do practical experiments with that. Right? Okay, yes? You said 4, you had 4, right? Okay. You can ask more, but no.
Correct me if I'm wrong, but I think for the color shading, we write this as stealing some kind of thermal motion. And then derive the like wave number also in some kind of like assumption, but then we look at cold plasma. Does it still hold?
All right. While I was going through that, I was waiting for complaints. All right. It's true. We started out from thermal distributions. But then we made a Taylor expansion. And then we forgot about the thermal distribution again. Okay? So we started out from these thermal distributions. You're perfectly right. By the way, there's a sign error. Okay, good. Fortunately, the sign error appears twice and cancels each other. So, all right. But at this point here, we have linearized the difference. Okay. If the plasma is very cold, then these numbers are very large, even if the potential energy is small. Right? So then even very small fluctuations of the electrostatic potential make our Taylor approximation break down. Okay? So, yes, it's true, we start from thermal distribution. At this point here, 4.5, we have already forgotten about them. Assuming that KBT is not too small, because then you can't do Taylor approximation to first order again. All right, and then you said we defined the Debye wavelength with the temperature, that's true, but then did not use it for the cold plasma. But we use the plasma frequency. The plasma frequency, however, does not contain the temperature. So, what I think I can claim is that when we later used these scales here in order to describe cold plasmas, we did not use the Debye wavelength anymore, but the plasma frequency. Okay? But you spotted a weak point in the argumentation. That's perfectly right, yes. Yes.
One question regarding last week's lecture on standard protection. There's a discrepancy between the results from the lecture and the factor of large, I think.
Yes, I noticed this as well. And
I think actually this time the book makes more sense, which is rare.
I agree with you. I agree with you. I noticed this while I was on the board, and I didn't want to waste any time searching for the mistake. But I think there was a mistake in my derivation and not in the book. I redid the derivation in the book, and there are two possibilities, of course. Either in doing so I made the same mistakes, or I found it correct. So I think the formula in the book is correct. And of course I can prove this by authority, right? Going back to Chandrasekhar's work.
We had like one encounter of the virtual particles that we had to calculate back to what actually happens to mass having.
Yes. Apart from that, the derivation on the board was much more clean than here, right? Because here I just inserted the ellipticity too early, and then you have all these clumsy terms. The content doesn't change, it just looks better. All right.
It seemed to me so far that we use the collisionist-Boltzmann equation and the Liouville equation kind of interchangeably. Is that correct, or do we make some underlying assumptions in some case that I just lost track of?
Okay, so the question was about my use of terms: Liouville equation, collisionist, Boltzmann equation, Vlasov equation, blah, 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 whatnot. I think the term Liouville equation is safe. It just says absolute dFdt is 0. Now you realize you need to do something on the right-hand side, and I think when you include arbitrary collision terms, you call this Vlasov equation. Then if you make Boltzmann's Ansatz, namely that collisions are given essentially by the product of densities, taking or not taking correlation between them into account, then you call this Boltzmann equation. And if you then drop the collision term again, you add the collision-less Boltzmann equation, which then turns into being synonymous with the Liouville equation. I think it's correct that way. I'm also quite sure that there are colleagues who use this differently. But what I mean is, collisionless Boltzmann equation is identical to the Liouville equation.
In the section about plasma physics.
About what?
In the section about plasma physics.
Plasma physics. Yeah.
We briefly discussed ion acoustic waves.
Yes.
And in the derivation, we assume that the electrons have a low frequency, the ions have a high frequency. For me, this is a contradiction with that the ion mass is much higher than the electrons.
This is not in the book. Ah, wait. Then we mean something different. Okay. Guide me there. Where do I have to go?
I didn't find it in the book.
You did not find it in the book. Yeah, that's right. So this is a section from Ishimaru's book, the Ishimaru I mentioned, which I thought is pretty interesting. And since I had some time left in the plasma physics part, I put it in there. I need to look it up. The idea is that the plasma frequencies for the two species are vastly different, and you can sit in between. So let's see. Plasma frequency is this. So the plasma frequency for the ions is very much lower than the plasma frequency for the electrons. So you can be above the plasma frequency for the ions and very well below the plasma frequency for the electrons. That's the situation I wanted to discuss. I hope that's what I said. There's no guarantee for that. further things. As I told you in the beginning of the lecture, it's a mistake to publish anything, but what can we do? Yes.
This might be a stupid question, but the third term in the response function decomposition that we did, like how can there be something not transversal or longitudinal? In which direction?
Where are you? In the thermal case or in the magnetized case?
I think it was around 4.266, where we derive this term proportional to p hat.
Sorry?
Oh, like
66, you said?
266.
266. Okay. That's pretty far down.
Maybe that was also the difference.
266, sorry, not 26. This one?
Or like in general, I mean that's an example where we've got the like epsilon from the parallel transverse and then the p term. I think we derived the p term somewhere earlier, but like how the term that's not neither parallel nor perpendicular to something. I mean, okay, yeah. I mean, I could split this again, right? I could split the term again.
Yeah, all right.
No reason not to want to complete this.
Now here we are in the case of magnetized plasma. So first of all, yeah, I think the cleanest answer I can give is the following. Waves that are transverse do not need to stay transverse. And waves that are longitudinal do not need to stay longitudinal as they propagate. And I think what gives rise to your confusion here, which of course is partly due to the way I have described it here, is due to the fact that if you look at a propagation matrix like here in 4269, it very clearly shows that longitudinal and transverse modes are being mixed. And this, I think, gives rise to the confusion. And I realize that I need to rewrite the whole section here. Because a clean separation between longitudinal and transverse is not possible here. Unless you orient the magnetic field with the k vector or perpendicular to it. And only then can you cleanly split the two modes. And when we further down discussed Faraday rotation, that's exactly what we did, right? We aligned the magnetic field with the propagation direction, and then you can cleanly split between the two modes. Otherwise you cannot, because they keep being mixed here by this propagation matrix.
I think that's probably right. What I meant is in 4.24 to 242.
242. That would be here. Ah, okay, yeah. You have a rotational part. So there's a part that is spanned by an antisymmetric tensor. It's this. Where are we? Yeah. It's this object here, right? It's this antisymmetric matrix. And this cannot be split by any of our projectors as we had introduced them before, right? Because they are both symmetric. So this means that when you set up the propagation matrix, this M matrix here, you need an additional, or later the matrix that that finally led to this expression here. You need to have a part that is purely longitudinal. You need to have a part that is purely perpendicular. And you need to take this part into account, which gives rise to differently propagating circular polarization modes. Right? So the B hat is there for covering circular polarization modes in addition to the longitudinal and perpendicularly polarized modes. All right? Yes.
I have a question to stellar dynamics.
Uh-huh.
And we did the analysis and found out that self-gravitating systems are not in equilibrium or not equilibrium systems.
Yeah.
And that we then did a perturbation analysis right after that and assumed we have a background.
Okay.
Doesn't this contradict the result we got before?
No, because you only need to assume that the evolution timescale of the background solution is very much longer than the evolution timescale of the perturbation. So the fact that we do see galaxies and galaxy clusters and so on shows you that stellar dynamical systems can have long-lived transient states, even though these are not equilibrium states. But this means that there is a timescale for the evolution of the entire system, which is very much longer than the time scale the system needs in order to respond to perturbations. By the way, if you wonder about the exam, as you saw, if you experienced, the lecture had 5 parts, right? This suggests a certain symmetry. For what? The cheat sheet. Okay. Honestly, I don't care.
Okay.
I don't care because I think that if you prepare this sheet on your own, this is an important part of your preparation. Now, once you have done it, well, bring it along. Don't bring the entire book. That would be unfair, and it would also contradict the purpose. Right? The purpose is that you do something on your own, in order to prepare, and then it's perfectly fine by me. If you start sharing that, right, and then you spread your own copy to n-1 other people, it's also contradicting the purpose. But as long as you do something that is in agreement with that purpose, right, prepare yourself. That's perfectly fine. I just don't care. Yes. Uh-huh.
In the derivation, you said that the factor and psi are small quantities, but when we then did an example for this, we inserted the atmospheric pressure for the pressure, and I'm a bit confused how this
Well, not the pressure is assumed to be small, but fluctuations of the pressure. There must be a picture, yes, there is. So the idea is that in this very, very schematic thing here, is that the amplitude of zeta is a small perturbation of the overall height of the layer.
And the pressure in the equation is then T0 for the unaffected.
Yes. Yes. That's what equation 3, 412 is meant to say. Right? The temporal fluctuations of psi and the fluctuations zeta of the boundary layer are supposed to combine in such a way that P0 is a constant. Anything else? Not the case? Yes.
One more question for stellar mechanics. At the very beginning, we derived the gravitation time scale. It's not a very specific question, just feels weird to me. Because we assume calculated it for one mass that is moving and all of the other masses are like static. And for that we found, okay, it's most of the time it can be assumed to be collision. Then we did that calculation. And with there being other masses responding to the moving mass. I mean, then we obviously had collisions. Because, I mean, that is kind of
Not necessarily. Not necessarily, because it's true. When we derived the dynamical friction formula, we looked at the hyperbolic orbits that individual masses have. But when we separate between collisions and not in Liouville's equation, the idea is that everything that you can describe by a Hamiltonian goes to the left-hand side. Everything that you would describe by a direct encounter of particles, for example, you would put into the collision term. And then, to some degree, it's your choice how you split up the Hamiltonian okay, you can have a non-Hamiltonian contribution, so for example, a discontinuous contribution to the collision terms, then it's obvious. Then you could split the Hamiltonian according to scale into a rapidly fluctuating part and a smooth part. And then you could again split between a collisionless Liouville equation and a collision term that would then contain the rapidly fluctuating part of the Hamiltonian, and so on and so forth, right? So essentially you are assuming that you can describe the motion of the particles with a sufficiently smooth Hamiltonian if you say that the equation does not contain collisions. And then if the system is, so to speak, thin enough, and if you do not have strong and small scale fluctuations in the potential there, you can still assume that this is a collisionless equation because the Hamiltonian is smooth enough. Yeah, well,
if I imagine the mass is very high, the mass of other particles is very
yeah, that's
receiving shot and stuff like that, so that would be a very low scale.
you could have that, but we are assuming that we have very many small masses because then their combined gravitational potential is essentially a smooth function. Right? It's a very fine-grained function. And yeah, and there we took the complete dynamics of the small masses into account, right? Because we used the hyperbolic orbits. And that contains the slingshot effect. Right? We just made a later approximation there. Did we do that? Not necessarily there. So our treatment in the derivation of the Chandra-Shekhar formula takes into account that small masses can completely escape, right? Because their hyperbola branches can disappear in infinity.
Also, maybe not that important example. I don't quite remember. I think we did in the exercise we did the Taylor approximation for small y, was it? And the y that y that we looked at. Sorry, wrong class. The Weber function.
For which function? Which problem sheet do you mean?
Regarding the dispersion relation using the
The Fadeva function.
But we did that for small y. And
This.
in the lecture, we also had a series approximation for large y. I was wondering how we tried the series approximation for large y.
This is way more difficult. And this is why I dropped this from the exam. How do you do that? I think the point is that you do a transformation from y to 1 over y and then make a first order Taylor expansion in 1 over y. I think that's the trick in doing that. But honestly, I just had no time to do this again. So I thought, okay, let's just drop it from this problem. It's not a good explanation, I understand, but I need to do this myself, and then I can send you a copy if you remind me of it. Yes.
When deriving the dielectric response function for the cold capacitor, we had to work with a matrix that shows the symmetry-based answer. So this, why did we not have to consider the symmetry breaking by the direction of the when?
We did. So we are here, right? And you see, my ansatz for m to the minus 1 does contain the symmetry breaking part. This one. All right? True, if you leave this out, you can't solve it that way. Do you agree? So this function c here that quantifies the asymmetric part. Yes. Yes, it is. And this is very important for cosmology. So it is polarized because the Thomson scattering cross-section is anisotropic. Right? So if you irradiate a given charge with differently polarized light, the radiation pattern depends on the polarization direction, and therefore with Thomson scattering you can create polarized radiation.
And with unpolarized light is scattered?
Also then, if the unpolarized light is not isotropically, has not an isotropic intensity around that charge. I mean, suppose you have an electron here, and it's being irradiated with unpolarized light from all around, but the intensity of the unpolarized light changes with direction. For example, let that be brighter here and less bright here, and so you have a quadrupolar pattern. And then you observe from there. No, you observe from there. So, all right. So the fraction of the light from here that's scattered in this direction is, or the intensity is a little bit higher than the light scattered from here. But the scattering cross-section is direction sensitive. So you get a little more from here. And this gives rise to a net polarization. In other words, if you irradiate the Thomson scattering electrons with an intensity pattern that is quadrupolar, it has a quadrupolar anisotropy around this electron, the Thomson scattered radiation that you get from there will be polarized. To a small degree, but nonetheless. And this is extremely important for the cosmic microwave background, right? Because there you do have that situation that the Thomson scattering electrons are being irradiated with radiation that does have a quadrupolar anisotropy around these electrons. And so in addition to the thermal the unpolarized, purely thermal intensity fluctuations that you see in the cosmic microwave background, you see on top fluctuations in the linear polarization. The cosmic microwave background is due to this effect only to 10% polarized. So the intensity of the linearly polarized radiation component is approximately 10% of the unpolarized component. But this is very well measurable, and it has been measured, and it adds very important information to cosmological information to the signal that we can extract. And now suppose you have a magnetic field, then you get a circular polarization component. So people have been frantically searching for that and didn't find it yet. But the linear polarization has been found, measured. The same thing, for example, if you take a photo of somewhere where you see the reflection of light from a window or so. With a polarization filter, you can take this away. Same thing here. You get polarization by reflection. Well, it's not exactly the same thing, but a similar thing. All right. Enough for today. I'll be back on Wednesday. If you are here, we can go on then. If you are not here, I'm going to leave. All right. Good, then, maybe see you on Wednesday.